We'll take a look at this problem. It says the 12 kilogram slender rod is attached to a spring which has an unstretched length of 2 meters. If the rod is released from rest when theta is 30 degrees, determine its angular velocity at the instant theta is 90 degrees. So let's take a look at this problem. So let's think about this problem for a minute. Let's think of maybe the strategy that we're going to use for this. And when you think about this, we're going to have a potential energy for the weight. And so we're going to need to see where the weight is below the datum line or above the datum line is the beginning and the end. So need to determine, and actually it's going to be the center of gravity. In fact, if you look at the problem again, the bar is at 30 degrees. And so its center of gravity is like below horizontal. We'll probably end up making the horizontal at the top there, the datum line. But in case, we're going to need to determine where the center of gravity of the bar is at the start and at the finish. And then for, again, also potential energy for the spring. Same idea. Need to determine the amount the spring is stretched from the unstretched length at start and at finish. And so actually, we're going to make, first of all, in other words, do this, we're just going to basically see, okay, how long is the spring when it's in the original position, how long is it stretched out? And then eventually we'll subtract the unstretched length. So we're going to figure out, okay, how long is the spring stretched at the beginning? Then also when we're at the end, the spring will end up looking something like this. What's that length going to be? So these are going to be the two things we need to figure out at first: where the weight is at the beginning and the end in relation to the datum line, and how long is the spring at the beginning of the end and the end. And I'll probably end up doing these maybe a little bit out, or I'll probably do the spring at the beginning and the weight at the beginning, then the spring at the end and the weight at the end. So it looks something like this. And we're going to need to do a little bit of trig on this because we're gonna have to figure out what the length of this spring is at the starting point. So we're gonna need to know this distance here at the start. At the finish, we won't have a problem because we can just use it'll end up being a right triangle. So let's take a look at some things here then. So if we take a look at this triangle here, if this is 30 degrees, of course, this total is 180. So that means this is going to be 150 degrees. And then, again, this is 2 meters. This is 2 meters. And so we don't have a lot of other information. So we're probably going to have to use the law of sines, say, to find, let's call this D1. So again, the law of sine, it could be law of cosines, I guess, huh? We'll have to use the law of cosines, which says D1 squared is going to be equal to the other two sides squared minus 2 times the other two sides, and then times the cosine of the angle between those other two sides. And that's going to be cosine of 150 degrees, like this. And then if you put all that in your calculator, you get this D1 to be 3.86 meters. And so we're going to have to see here. And we're also going to need to figure out where the center of gravity of our bar is. And remember, our bar is this one right here. And so let's take a look at that. So again, if you look at the bar, now we know that that's 30 degrees from the horizontal. And halfway down, that will be 1 meter. So this is the bar that we're interested in, this bar right here, that it's 2 meters long, and its center of gravity is going to be, again, right in the middle, right here. And so we want to find out where the center of gravity is at the beginning when the bar is at 30 degrees. So we can just use the right triangle and say that that's going to be D2 is going to be 1 sine 30 degrees. And that's going to be 0.5 meters. And so if we call this line right up here the datum line, that gives us some more information. So at the start, our spring is going to be stretched 3.86 meters. And the center of gravity of the bar is going to be 0.5 meters below the datum line. So again, this is at the start. And let's look at the finish. How's things going to end up? And of course, it's going to look something like this. Actually, this is going to be a lot easier to work with when it's at 90 degrees. So it's going to be 90 degrees. And our bar right here is going to be 1 meter below the datum line that we've defined it. And I'm just showing that this is a right angle here. And now we can also find this right here because we know that this is 2 meters. Again, this is 1 meter below, although this whole side is 2 meters long. So let me call this D3. And so that's just, again, D3, call that like that. And we can actually just say that, again, if this is 2 meters long, this is 2 meters long. So this is going to be the square root of the sum of the squares of the other two sides. And that's going to be 2.828. And then finally, we want to know where the center of gravity is, but that's pretty clear. That's going to be this 1 meter. Let me just call that a D4. Like this. So again, this is the length of the spring at the end. And this is the center of gravity of the bar. So let me mark these. So again, this is the spring length. Center of gravity of bar below datum. Once again, this is the spring length. And center of gravity of bar below the datum. And so we have the information at the beginning and the information at the end. And we're going to need to know the mass moment of the rod. And again, since it's a slender rod, this is going to be 1/12 ml squared. And it's going to be 1/12. And the rod is 12 kilograms. And its length is 2 meters. And when you put that on your calculator, actually the 12s will cancel. So this is going to be 4 kilogram meters squared. And now we want to find the mass moment about this point A, because that's a point about which it's rotating. So let's find that about A. We'll have to use a parallel axis theorem. Now the center of gravity is 1 meter away from point A. So this is going to be 4 plus 12 kilograms times 1 meter squared. And obviously that's 16 kilogram meters squared. And we have most of the information we need. So we just have to organize this. Again, you can organize this in whichever way you feel. I'll maybe make it something like this. And say, okay, we have like a start. And at the end or the finish. And now to start, nothing's moving, so we can call the kinetic energy 0. And at the end, fortunately, everything we've found this about the axis of rotation. So we can use the basic formula that's 1/2 I, in this case, A omega 2 squared. And that's going to be equal to 1/2. And we've just found that up above 16 times omega 2 squared. So T2 is going to be 8 omega 2 squared, like that. And now we want to find the potential energies. And so at the start, we have to go back and look at our previous thing here. So the potential energy for the spring, remember for the spring, the potential energy, I think we call that E, is equal to 1/2 spring constant times S squared, where S is the amount that it's been stretched, the spring. And so in this case, we have 1/2 40 newtons per meter. And the amount it's been stretched was 3.86 minus the unstretched length. And put that in your calculator. And that comes out to be 69.192. And then the potential energy for the weight is going to be the weight times Y. Now, this time, remember, for potential energy, this Y is the value either above or below the datum line. And if you're below the datum line, it's going to be negative. And so in this case, we have a weight of 12 kilograms, 9.81 meters per second squared. And then, if you recall from before, at the start, we're 0.5 meters below the datum line. And this comes out to be 58.86 Newton meters. Again, that's negative because it was below the datum line. And now let's look at the end. We'll do the same thing. Find the potential energy for the spring. Again, as I said, it's 1/2 K/S squared. Again, S is the amount been stretched from its unstretched length. And so it's going to be 1/2 times 40 Newton meters. Now this time, at the end, it was stretched total 2.828. So that's going to be 2.828 minus its unstretched length. And put that in your calculator. This is going to be 13.71 Newton meters. And then potential energy for the weight. Again, it's going to be negative because it's still below the datum line. It's actually even farther below the datum line now. And remember, at the end, it was 1 meter below the datum line. And that's 117.72 Newton meters. And so I think we have almost everything. I think we do have everything we need. Now use the conservation of energy. T1, capital V1. And these were actually all capitals here too. Equals T2 plus capital V2. And again, we said kinetic energy was 0 plus the potential energies 69.192 minus 58.86. Then T2 was 8 omega 2 squared plus 13.71 minus 117.72. And when you solve for omega 2, actually omega 2 squared, you get something like 14.293. Then if we take the square root, it's around omega 2 is 3.781, I guess. And that's the answer. Let's take a look at this problem. A 40-kilogram wheel has a radius of gyration about its center of gravity of 250 millimeters. If it rolls without slipping, determine its angular velocity when it has rotated clockwise 90 degrees from the position shown. The spring AB has stiffness of 100 Newton per meters and unstretched length of 500 meters. So let's take a look at this problem. So we're going to have to calculate the normal things. We're going to have to calculate the mass moment of the wheel. And we're given the radius of gyration. So you remember that's going to be m kg squared. And it's 40 kilograms times 0.25 squared. Because we're given the radius of gyration of 0.25. 0.25. And this comes out to be 2.5 kilograms per meter squared. Now remember, this is a rolling wheel. It's not fixed at the center. So we're going to want the I about its instance center. Remember, the instance center is going to be right where the wheel is touching the ground. And the center of gravity we calculated here is about this point. So if we want to find this about the instance center, it's going to be this value here, 2.5, plus the mass, 40 kilograms, times the distance to the instance center. And remember, that's going to be 0.4. Because this was found about the center of gravity of the wheel, but we wanted about the instance center, so we do this. And we put all that in your calculator. That's going to be 8.9 kilogram meters squared, like that. So the wheel is going to roll clockwise 90 degrees. So let's think of what we have here. So we're going to probably have to do a few pictures again at the start. It's going to, we have a picture, something like this. And also another complication is the spring is not in the center. Then at the end, it is rotated. Now, since it's going 90 degrees to the right, obviously this point right here where the spring is connected, I think is what is called point B. Again, this was point B. So at the end, point B is going to come down over to here like this. Again, remember, after 90 degrees, or pi over 2. So then the question is, how far has the center moved? So the center is moved. We said this in earlier video that the center will have moved a distance of r times theta. And again, the radius is 0.4 meters, and it's rotated pi over 2. So this is going to be 0.625 meters to the right. And again, that's how far the center is moved. So now, then the question, where is B at this time? So let's think about this. So originally the center was 1.5 meters. So now it's moved this far to the right. So the center then of the wheel, again, here's the center and here's B. So the center, let's say from this barrier here, that's going to be our original 1.5 minus the distance it's moved. And so that's going to be that's going to be 0.875. So it's 0.875 from the barrier. But now B, the distance between the center and B is 0.2. So it's a little bit closer. So B then has got to be 0.875 minus 0.2. So it's going to be 0.625, like that. So now we're going to have to look at the spring. Because again, since the spring's not in the center, it kind of complicates things a little bit. So again, at the start, we're like this. Now at the end. So now the spring looks something like this. It's stretched like this. And again, see, B has dropped down 0.2 meters. And now, remember, originally when B was up here, the spring was horizontal. But now B has dropped down 0.2 meters. So this side is going to be 0.2 meters. And we determined up here that this dimension is 625 meters. Like this. And so this length here, I don't know which one to call it, you just call it S, is going to be the square root of the sum of the squares. And that's going to be 704 meters. So that's going to be the final length of the spring. So now I think we're ready to do all of our calculations. So again, let me put another start and finish here. So again, that's the start. Theta 0 at the end. Theta is 90 degrees. And then at the beginning, T1 is going to be 0, no initial velocity. T2 is 1/2 I omega squared. And we calculated I about the center of gravity to be 8.9. And that's going to be 4.45 omega squared. And now we'll have to look at the spring energy. Now we don't have any, no other potential energies because nothing is dropping or being raised, because the center of gravity of this wheel is always going to be the same. It's always going to be at the same height. So the only energy, potential energy we're going to have will be due to the spring. And again, that's always 1/2 K S squared. And 1/2, that was 100 newtons per meter. And then the original length was 1.5 at the start, but the unstretched length was 0.5. And when you calculate this, this is 50 Newton meters. And then at the end, again, it's going to be the same thing. 1/2 KS squared. Maybe 1/2, once again, 100 newtons per meters. And now this time, Again, the final length of the spring is 0.704 minus the end stretched length. And when you put all this in your calculator, this comes out to be 2.0808 Newton meters, like that. So now use conservation of energy. T1 V1 equals T2 plus V2. Again, no initial kinetic energy. Then initially we have 50 Newton meters. And at the end we have well, actually, I guess I should put the kinetic energy in. 4.45 omega squared plus 2.0808 Newton meters. That comes out to be omega squared is 10.6, and omega is 3. I probably rounded a little bit too much here, but end up with 3.26 radians per second. Could be that, or could be a little bit higher. May rounded a little bit too much. Let's take a look at this problem. The slender 6 kilogram bar, AB, is horizontal at rest and springs unstretched. Determine the stiffness K of the spring so that the motion of the bar is momentarily stopped when it has rotated clockwise 90 degrees after being released. So this one's a little bit different, is that we have to find the K value such that when this bar gets to 90 degrees, it's going to stop. Now, it'll just stop momentarily, of course, and then it'll probably come back up the counterclockwise direction. So let's take a look at this. And so we're probably used to this now. Might as well go through and find the usual stuff. Find our moment of the rod. We only have one part really that has a mass moment. So again, about the center of gravity, again, you think about G here. About G, this rod, again, it's a slender rod, so it's going to be 1/2 ml squared, excuse me, 1/12 ml squared times 6 kilograms. The length is 2 meters. And when you put that on your calculator, you're going to get 2 kilogram meters squared. But of course, that's the mass moment of this bar about its center of gravity. We want it about A, because it's going to be rotating about A. And so it's going to be this value. Using the parallel axis theorem, it's going to be 6 kilograms. And the distance to the center of gravity is going to be 1 meter. And that looks like that's going to be 8 kilogram meters squared, like this. And I think that's really all the all the stuff we're going to need. So again, again, you can organize this in your own way. Again, at the start, I'll put like at the start. Like this. And let's maybe call this axis the datum line. Again, that's going to be like where A is, the horizontal with A. And then we're going to have our end. And again, this bar is going to go all the way down here. So we'll have a picture, maybe something like this. Again, A is still up here, and B will be down here. And then C, where this spring is attached, is up here. Something like this. And again, I remember this is 2 meters. So, of course, the center of gravity is here. And then it's going to end up going to here. And now this whole thing is going to be 2 meters long. That's how long the bar is. And what else do we know? We know that this distance from C to A is going to be 1.5 meters. Like this. And so we can actually find then this distance here. Remember, this is the distance that the spring is stretched. That's the spring is between B and C. So we can find this because we actually have a right triangle here. And then we know that this side here, also, we know one more thing. We know that this is going to be 2 meters up here, huh? If you look at our original setup here, C was 2 meters from A, and then horizontally, then vertically it was 1.5 meters from A. So we know that this side over here is going to be 3.5. And this side over here is 2. So this is going to be 4.031 meters. It's going to be the length of the spring. So originally the length of the spring, remember, that's going to be 1.5. Then it's going to be stretched to this value. And also the center of gravity was at 0. Now, when it's over here, it's going to be, 1 meter below the datum line. So let's go ahead and do our energies. Once again, one thing nice about this one, at the beginning, it has no velocity. And then also we want to find the point at which it stops momentarily. So our kinetic energies are 0. And now at the beginning here are a spring is going to be spring energy 1/2 Ks squared. But, and you really don't even have to write this down. Because you remember we were told that it was unstretched at the beginning, so we can just put 1/2 K 0 squared, that's unstretched, so that's going to be 0. And then also, our weight at the beginning is on the datum line. So again, that's weight times y. That's going to be 0. So we don't have any kinetic energy at the beginning. And our energy at the end is going to be, again, 1/2 times K, which we don't know yet. And then it's stretch 4.031 minus the unstretched length of 1.5. And so that means our potential energy, when you put that into your calculator, we get 3.203 times K. And then the potential energy for the weight, give me weight times y. And now we know, in this case, at the end, it's going to be 1 meter. What the center of gravity is going to be 1 meter from the datum line. And it's going to be below, so that would be negative. And when you put that in your calculator, you get 58.86. Again, remember that it's negative because it was below the datum line. So now we can put everything into our conservation of energy. T1, V1, T2, V2, 0 plus 0 plus 0, 0, and then the potential energies at the end are 3.203 K minus 58.86. And when you solve the spring constant K, you get around 18.376. I don't know, we can call it 18.38 Newton meters. That's going to be the spring constant. That's the spring constant that you need for the bar to stop right when it gets to 90 degrees.